Very good evening to all of the participants. Let me share my screen and let it start the presentation session. Then we will start the demonstrations. So I hope my screen is visible. Am I audible to all the participants? Confirm?
Yes, sir.
Yes, sir.
Yes, sir.
Great. Great. Thank you very much for the informations. So I would like to inform myself, Anil Sharma, today's speaker. So I will introduce about the objective of this FDP and whatever the other titles that will cover up in this next 5 days. So basically our main objective is just to promote, to make familiar with the latest technologies. So in this regards, today's I will perform the basic materials calculations, the presentation session, the materials modeling, material simulations, then the device simulations in tomorrow's session. My other colleague will join the session, which will be delivered by Ujjwal Pratap, Sahil, Darshan, and Dr. Ali. So there will be 5 speakers in this FDP program, where we will educate all the information related to semiconductors, nanotechnology, quantum technologies, material simulation, device simulations, simulation purpose, experimental, everything will be covered up today. Okay. So let's start the sessions. Thank you very much for the joining. So I want to start a small presentation session, then we'll go for the live demonstrations. So we Impulse Technology that are located in Delhi, near about this Gurgaon locations. We are the partner of some softwares and some experimental company. One of our partner is called Nano Academic Technology. That is basically a Canadian company, and which developed the software for material property predictions, next generation material, next generation nanoscale devices, transistors, and quantum devices applications. So based on density functional theory, non-equilibrium green functions, finite element model-based simulation tools, the company are developing the softwares. And apart from this Nano Academic Canadian company, we are another partner that is called this Fluxim. So this Fluxim is Switzerland-based company. They are located in Switzerland, European country, which developed the simulation software specifically for solar cells and LED application and equipment for the characterizations. Single click equipment are there, which can measure the electrical, optical, emissive property, and simulation tool is also there for theoretical applications. So if you look into this SETFOS, LAOS, these are 2 simulation software, and other are equipment for electrical characterization, ELPL measurement, perovskite solar cells, stability degradation analysis of different type of solar cells and LED. Even we also have some small chambers, probe stations for thin film characterizations. So multi-probe stations. This is 4 probe, 6 probe chamber. That is for thin film application, and 2-stage chamber is also there, which can work for thin film as well as solar cells applications. So we have a complete solutions from material characterization, material simulation, device simulations, solar cell, transistors, and many wide range of application product that we are delivering to the market. So this is all about our company and our partners' informations. Let's discuss the today's session that we will discuss about the Nano Academic Technology, about their product and how this software, these product can help you to achieve your research goal, whatever type of materials application you are working on. So that material specific property predictions, we will start here, because every device will be formed from the materials. So material is a major important to make the device structures. That's why I will start from the material property predictions. So this Nano Academic Technology was founded in 2008 by Dr. Hongo, Dr. Zhu, and Dr. Lee. They are located in McGill University, Canada. The software was developed for quantum transport calculation, initially for device calculation, DFT plus NEGF. And later on, they also developed the density functional theory along with the perturbation theory implementations. Because the material property predictions, material accuracy is also important when we simulate the device structures. So device simulation, material simulation, even recently they are determining to address the emerging center of quantum computing. So quantum technology simulation tool, spin qubit in semiconductor devices, quantum material-based device-based application, quantum TCAD tool they have also developed, which can work on quantum spin qubit applications. So let me discuss about their different product in details. Then we'll go for the live demonstration where I will share my screen to you, and then you will see it, how the tool will look like, how you can quickly model or manipulate different atomic structure positions, and how the simulation can be performed, and the visualization of your output and the data extractions. So we start from this first module that we can say a first background calculation engines that is called Rescu. So this Rescu is basically a real space electronic structure calculator. It will basically solve your density functional theory. So if you are known about density functional theory, it is basically a background equation solver that will solve the Poisson DFPT package, and it will solve your material electronic structure property calculations. And later on, they also developed this density functional perturbation solver. So density functional theory is there for electronic structure calculator, and for Raman properties, optical properties calculation, they added the perturbation theories as well. So for the perturbation theory included in the tool, which can calculate all your response functions. So polarizations, Phonon band structures, optical properties, Raman properties, energy loss, and many other type of calculations can be performed at materials levels application. We are talking here about the material property predictions only. So this Rescu real space electronic structure calculator is a very optimized tool where complete large scale density functional theory can be calculated, and it can predict various material property, Raman property, optical property, and other response calculation with Phonon calculations function is also there. So this Rescu is basically written in MATLAB and C. This is MATLAB and C combinations. The tool is written in MATLAB C, where you can focus up to 10,000 atom calculations for large scale calculations of material predictions. It also implemented the perturbation theory for dielectric tensor calculation, dynamical matrix, dielectrical permittivity, refractive index, real imaginary part of NK data for the optical property analysis. This tool can also calculate the optical property. That optical property can be used in the device simulations also. And then Raman calculation, Raman tensor, spectrum, IR intensity, and many advanced functionals are there. As you know, for the material property, whenever you work on the device application, you require some material, and that material contains its own properties. So the property, what will be calculated by the software, it includes the advanced functionals. Advanced basis sets are there, hybrid basis sets are there, Hubbard terms are there, and many exchange correlation functions, basis sets, some meta GGA, hybrid basis functions are included. And based on that hybrid functions and DFPT theory, it can accurately predict your materials characteristics. So all electronic analysis like density of state, projected local density of state, Phonon local density of state, band structure, band and folding, charge analysis, molecular populations, and many other analyses are there, including nonlinear optical susceptibility, spintronics calculation for material specific, spin up, spin down calculation, non-collinear spin orbit interaction is also there, SOC is there, Phonon tool calculation is there, and large scale CFSI solver is there, which can solve your material property predictions accurately. So this is brief idea about this capability of this particular tools. So if you are interested in only material specific application, you are working on nanomaterials only, then this tool I believe will be very useful to find your optical, Raman, and electronic calculations. Whenever you will work on device applications, because many people work on directly device application, many people work on material property prediction first, then will go for the device. So we also have the device simulation package that is called Nanodcal. So Nanodcal is basically nano DFT calculator or nano device calculator. It is also written in MATLAB and C, where it is also used in many publications. If you will Google Scholar on this Nanodcal, by typing this Nanodcal on Google Scholar, you can find so many publications. So it majorly can also focus the material property as well as the device properties. Basic material property can also be calculated by this Nanodcal tool, but not more advanced functionals are implemented. So for advanced functionals, you require the Rescu. For Raman property, you require Rescu. For optical property, you require Rescu. And for all response function related perturbation theory, the Rescu tool is there. When you go for the device application, then this nano DFT tool is there, which can work on device related application, where you can define some electrodes, you can apply some biasing, some voltage biasing on your contact, and then you can plot the IV characteristics. So that electrical property calculations, you require this Nanodcal tools. We have a complete package. We have a complete bundles also. Dependent on your requirements, we have multiple options. So this is like a device simulation package, which can work on 2-terminal devices, diode simulation, transistor simulations, and many other thermoelectric property, photodetectors applications, and other molecular electronics device related applications specifically. If you look into that, the electronic property is also there. If you want to work on only basic property without any advanced functionals, but majorly you are working on device specific application, then this Nanodcal tool is there. We will discuss much more about this particular Nanodcal by tomorrow, but today we will discuss about the material property prediction by using the Rescu softwares. If I talk about how the process will work, the workflow of the softwares. So basically there will be a 3 processing part. One is called the user interface that will help you to model the structures, where you can create one material file. You can create your crystal structure by defining lattice parameters, by defining the cell length, by defining the different ABC, alpha, beta, gamma, some space groups. So we have advanced building tools. In the building tool, you can build your structures. Suppose you do not have material files. You have some lattice parameters. So based on that lattice parameters, you can build your structures. If you want to get some material files in our library, we have a package of materials. We have a database of the materials. From there, you can also pick up your materials. So either you can choose the material from our own library, or there is some API interface with third-party tools, with third-party open source library. Let's suppose Material Project. Material Project is one of the open source library where all the materials database contains. So it can directly fetch your material through the API access, and it will add in our user interface. So there are couple of multiple options where you can build your structure, you can import your structures, you can upload your you are working on any other software, and let's suppose you have a material file in a PY file, in a HZW file, in a XCIF crystallographic information file, XYZ file, or any other extensions. That material file you already working. Still, there is also provision where you can upload your existing material in our user interface. How it will be done, that I will show you in the coming session. Now, once you created your materials, whatever the manipulation, whatever the structure, either simple or complex structure you want to build, this advanced tool builder will be there that will help you to build your structures. Then there is an option called setup parameter calculator, where you can select your density functional theory parameters like electron temperature, basis sets, pseudo potentials, sampling point, iterations, damping factor, incoming photon range, and many other DFT parameter is there. Perturbation theory parameter will be there. that you have to select some parameter to run the job, to run the simulation theoretical analysis. So setup calculator parameter is there. Then once you run the simulation, there is a visualizer where you can visualize your output, and also you can extract your data. Whatever the output will be generated by the software, you can export all your data. Now, then there is a different kind of material: electronic, structural, optical, thermal, magnetic, electron phonon coupling. Many kind of material property prediction can be calculated, but not for the device specific, because the Rescu works on material, but we also have the provision for devices, those who works on device applications. So the Nanodcal tool, which I shown you, that can work on the device specific applications. So if you want to work on molecular structures, surface structure, complex structure, interface structure, that top all the kind of supercells, even different molecular can be built, some different crystal can be simulated, thin film material can be simulated. Even the interface of different material can also be simulated, and surface cells. If you will work on device application in future, then there is also provision. The Nanodcal can simulate your device related application. Sorry. So for device, two-terminal based devices, graphene based devices, and many other tool based devices, including molecular based devices, the Nanodcal tool will be helpful. Even we package all the module in a single bundles, that Nano Academic tool is specifically. Now, if we talk about what are the basic functionals, basic parameters for the material property predictions. So this Rescu contains the LDA, GGA, meta GGA. These are the exchange correlation functions. Hybrid exchange functions are there. Collinear spins are there. Non-collinear spin orbital interactions. Even EXX with partial exact correlation functions. EXX with correlations, meta GGA, GGA, and LDA, including the Harty words. So this type of exchange correlation functions are implemented in the algorithm, and you can select each parameter. Different other basis set will be there, which the user can select, and based on that, you can run the simulation and get your property predictions. If we talk about the analysis part, all the symmetrical analysis, structural relaxation, optimization is also there. You can optimize your structure. There is one provision for structural optimizations, relaxation, band structure calculation, band unfolding, molecular population, density of state, PDOS, LDOS, Bennier functions calculations, and many more other analysis, including this is called neutral NAO basis and real space basis. Band structure is calculated for different two material, including the density of states. So this is based on real state electronic structure calculated. Neutral atomic database, neutral atomic objective materials are there. Based on that, it will calculate. Apart from density functional theory, it also includes the perturbation theory, the complete toolbox, or the response functions. So these response functions are there to the perturbation, electrical field application, atomic displacement, third order non-linear response, 2n+1 theorem is implemented, BICG and CFSI solvers. So for ion clamped dielectric constant calculation, vibrational mode analysis, low frequency optical calculation, non-resonant Raman spectra, non-linear optical susceptibility, and electron phonon couplings. So phonon band structure, phonon density of state, Born effective charge, infrared IR intensity, complex dielectric permittivity, refractive index, energy loss, oscillator strength, tensor, susceptibility, and other scattering time and mobility and other analysis. So related to the complex functions, this software can also helpful. Now, if we talk about some the DFPT ion clamped dielectric constant calculation, the optical property of different material. So this is one of the benchmark accuracy. The Rescu calculated for carbon, silicon, aluminum phosphide, silicon carbide, magnesium oxide. So by using this Rescu tool, numerical and experimental, so around 90%, 95% accuracy we can predict So there is CFSI solver is also implemented, which is also having its own advantage that will increasingly outperform as compared to the conventional solver. When the system size grow, whenever the material number of size grow, it will solve your algorithm very fastly. Algorithm more parallel, low memory requirements. So based on this comparison benchmarking, number of atoms, and this CFSI solver is implemented, which is 8 times faster in terms of simulation speed. So this number of atoms we have simulated on this 2.4 gigahertz processor for boron nitride dielectric constant property is calculated. So different material property we calculated numerical and experimentally. Now, apart from the optical calculations, not only optical property prediction, it can perform the Phonon calculation and density of states. When you work on different material analysis, as you can see, this is one of the diamond material Phonon DOS calculations with 8 atom, 64 atom, 216 atoms. So based on that number of atoms with respect to frequency and density of states is calculated with the Brilliant-Jones root points, and it is more like whenever the number of system size grow, number of atoms are grow, large scale supercell simulations, then our speed will be faster, and we can also calculate the Phonon related frequency spectrum as well. And if you want to work on low frequency, long wavelength optical analysis, then the dielectric permittivity. This is one of the comparison with respect to real part, imaginary part of wavelength and refractive dielectric permittivity. So this is called NK files, refractive index data, simulation and experimental, around 90% accuracy we can predict. So this is IR intensity and oscillator strength. Hexagonal aluminum nitride refractive index, dielectric permittivity are calculated. So material property, electronic band structures, Phonon band structures, optical calculation, and Raman calculations. These are the major things where the materials enhanced calculations can be done. We want to work on IR, infrared intensity analysis. So this is one of the perovskite material, CH3, NH3, PBI3, hybrid, organic, inorganic material are there. So this kind of atomic structure with different dopings can be introduced. You can also add some dopant, and around 48 atom per unit cell with full Phonon mode decomposition. We have calculated the IR intensity. So IR intensity calculated, and also as compared to the quantum X ratio, we also find some comparison that I wanted to show you here. Now this is all about different Raman and IR intensity and optical. Even this Rescu will work for noble material study for spectroscopic prediction and analysis. Like there is one silicon nanowire. This is one of the supercell structures. Okay. This is DFPT with 9R3C supercell structure. This is 3C and this is I9R and perturbation theory Q point. That is called incoming photons, outgoing photons polarization, and Raman intensity, photon wavelength, temperature, optical damping. This is DFPT parameters. Experimentally, with the combination of DFPT, 9R and 3C, both structure, and separate material phase calculations. So our calculation of the hybrid system correlate correctly so that the 9R phase dominate the low frequency mode and 3R phase the high frequency mode, which is at odd with the theoretical prediction for the isolated 3R and 9C phase. So corroborated with the experimental. So this is like Raman intensity calculations with our tools. So measurement with different measurement direction and simulations. So silicon nanowire study by using DFPT methods. So this is basically for different other analysis. Now, if I conclude the software that is called Rescu, which is basically a atomic structure calculation based on material for material analysis based on density function theory and perturbation. Now, in this FDP session, I will go to the live demo also in the Rescu, how you can model different material and how the property can predict it. But in the FDP, 5 days FDP, you will get to know about different other product. Maybe some other product could also be benefit for some of the audience. So we will also discuss about the SETFOS software for solar cell and OLED application. Even we will show you the information about these other product for large area PV module, AMOLED simulation, electric characterization, PLPL, electroluminance, photoluminance, angle dependent measurement by using philos, degradation analysis, lithos, and stability measurement of perovskite solar cells, MPP tracking, this litho slides. So we will discuss about these in details in coming slide, majorly on the SETFOS part. But if somebody interested in other product, then we also have some more discussion. We can discuss separately on different other product. Now, the today's session was Rescu. Even the upcoming plus version is also already developed for Python in Python language that can also work on material calculations. We will discuss tomorrow in Nanodcal and their plus version, and then coming session, the QTCAT for quantum TCAT spin qubit applications. And if you talk about the SETFOS software, that one of my speaker will discuss on day 4th, that basically for solar cells, organic solar cell, perovskite solar cell, tandem solar cell, heterojunction, thin film, quantum dot, OLED. So this SETFOS is specifically for optoelectronics domains, specifically for perovskite, tandem, organic, thin film, solar cells, and LED application with different excitons, ion transports, unlimited semiconducting layers, electrical optical characterizations. One of my speaker will also develop in this FDP program. So I wanted to show you about this SETFOS. So I request to all the participants, please be join at 5 p.m. every day so that you will get to know complete detail about each product. Even one of my speaker, Ujjwal, will also discuss in coming session about quantum TCAT tool for spin qubit in semiconductor applications, for confinement of single electron hole, for quantum qubit application. My colleague, this Ujjwal, will also discuss in coming days, and how the qubits can also be simulated by using quantum TCAT advanced quantum modeling softwares. So this is for quantum TCAT, quantum modeling software. In details will be discussed in the coming sessions. Even we also do provide the probe stations for experimental, those who work on experimentally on thin film application, on solar cells application, on different characterizations. So without needing of liquid nitrogen, we also provide the chambers for thin film sample characterization, 2 probe, 4 probe, single stage, 2 stage, thin film plus solar cells. LED lamp will also be provided, and water chiller is also there for cooling the samples. Even the sample holder is also there that can hold your sample without connecting your sample with the crocodile pins. So that kind of probe station for experimental, how you can characterize your samples and what services and product that we can deliver to you. So that will also discussed by one of my colleague, Dr. Darshan, in coming days. So this is all about the FDP programs. Even in any participants will have any questions after this FDP program today, even every day, every speaker will take your queries, and we understand your research objective that you want to perform, and whatever the help we can do, we will try to help you. Thank you for listening constantly. And this is all about the presentation session. Now I will discuss about the live demonstration, that how the Rescu software can help you to model your structure, to simulate your material property prediction from scratch. We have a 5 days. So please be join every day so that you will get to know a complete detail in all the product. I believe this kind of FDP will be very grateful for your research domains. Now I would like to go for the live demo on the software. So I would like to share my software graphical user interface. So I will take your question and answer session after 1 hour. Then we'll discuss on your problems also. So just a minute. I want to share my software. My C drive where I want to show you. So those who have installed the demo license, they can see this device studio applications. So I would like to double click on this device studio, which is available in device studio 2024. And inside that, there is some device studio graphical user interface icon. So I double click. I would like to start from scratch. So I will click on this create new project and click on OK. And I want to define the name of my project and the location of the project where I want to save this project. So let's suppose FDP as an example. This is my name of project. And then I want to save it. Let's suppose as an example, I want to save on desktop. So this is my graphical user interface. And this user interface, we will help you to model your structures. So now, if you see this user interface, there is also provision where you can click on this file option and then click on the import options. In the import option, there is an option called import local and import online. Now, import local means there is one library of material in my database. So if I click on import local, this is my local material library where all 0-dimensional material folder is there, 1-dimensional material, 2-dimensional material, 3-dimensional material, conductor material, insulator material, layer-based other material, magnetic material, oxide material, metal oxide material, some nobility material, semiconducting material. So each folder contains the database of the materials. Because many people work on silicon, many people work on MOH2, many people work on different other materials. So we have a material library. During the installation package, all the materials were stored in my database. So if I will select any material, let's suppose I want to work on MOH2. So XZW is the unique format of this particular company, this particular software. But if you have some other extensions, let's suppose you have some XYZ format, CIF format, XSD format, postcar, fontcar, SCF.input, relax.json, ab initio molecular dynamics.json, .as, .mol, .pdb. So based on different input file, whatever, if you already working on some different other crystallographic information, CIF file or XYZ file, that file can directly uploaded apart from existing XZW. This particular company have XZW, but other software file can also upload it directly instead of creating from scratch. So if I will select it, I can click on open and it will load the material in my database. So this is loaded in the dashboard. This is my material which I have selected from my library. Whatever the undesired materials are there, I will drag the rectangle by holding the right mouse button, holding the left mouse button, and then draw the rectangle and select all the atoms. So now all the atom has been selected. I can click on this zoom button and then hold the left mouse and then scroll the cursor up and down, and then it will zoom your atom. Now these atoms I have selected, which is showing with the yellow color. If I want to delete the undesired atoms, then I simply press delete atom button. So I can delete the particular atom which I don't want to use it, and then click on this 3D viewer selection mode, which will select particular atoms. If I click on this particular atom, I can delete it. If I want to click on this particular atom, I can delete it. So undesired atoms can be deleted by following the same procedures. Whatever the structure you created, if some atoms are added default or whatever the atom you don't want it, you can delete it simply by pressing this delete button. So delete button will help you to delete the atoms. Now this is one simple procedure. I can click on this home button so that it will go to the home. Different visualization is there where you can view in X by XZ, by Z, by X, ZX. Whatever the view you want to see your structure, crystal lattice, particular view, you can see it, whatever the visualization you want to perform. Now this is one way where I have added the material from my library. I have not created by material. I have not created material myself. I have just went to the file option and then I get to the import option and then click on import local. And in the import local, this is material library. Wherever I went to this 3D material and semiconductor and find MOS2 by pressing the M in my keyboard and the material I loaded it. So this is a simple procedure where everyone, if the material are available in my library, they can find the material in our database and simply you can start working on the particular material which you are doing your research. So this is one of the procedure where material can be directly uploaded. Now, let's suppose as an example, material is not present in the library. It can also be happen. The material which you are working on, it is not available in the library. In that scenario, you should go to the import, file, import, and then click on import online. So once you click on import online, there is one interface will open. And this interface is directly connected with some open source library like material project. And whenever you will type the formula, it will search that particular material. Let's suppose I want to work on boron nitride. So I will type the formula of boron nitride and click on search button. So through the API access, it will search the particular material combination, boron nitride, all possible combination. It will search online and give you the suggestions that whatever the related to the boron nitride, multiple combinations are there. It will select it and show it that related to boron nitride, these materials were found. And whatever the material you want to do your research with their different space group is also mentioned. So you can select the material and according to the space group, and then you can start add your material and work on it. Now I type this boron nitride and accordingly the information about the boron nitride is here. Like the lattice parameter, cell length, ABC value is there, alpha, beta, gamma is there. So this highlighted region that will display the cell length, ABC lattice parameter and alpha, beta, gamma. And when I scroll down, it will also display the boron nitride coordinate points. So this is the coordinate points and cell length parameters. So whatever you will select on particular element, that cell length it will display, alpha, beta, gamma, ABC value, and the coordinate points in the selected unit cell of the crystals. So that information, whatever the crystal it is selected right now, that information will display here. So this is one way where user, the material is not present in the library, then it can type that formula, search the material, and click on this add button. Based on this add button, it will add the materials. So now I click on it, this boron nitride material is added. Now similarly, if you want to add any other material, you can also do the same thing. So I click on this. Let's suppose you want to add, not directly import, you want to add another element online. So I click on this and click on import online. And here, if you want to, let's suppose you want to work on aluminum nitride. So I will search aluminum nitride and then it will search here. And whatever type of aluminum nitride you want to work, according to the space group, you can select that particular one. And click on add button. And this procedure will add the new materials. Okay. And then further we will select the density functional theory parameter and then we will run the simulations. Now let me try to define some other materials also. Let's suppose material is also not present in online mode. So online it is not available. Input local is also not available. The third option is called new, where you can click on this crystal options. If you want to make the crystal, you can create the new crystal. If you want to make the molecule, you can also make the molecules from scratch by defining the parameter. Similarly, the device also. So the materials interface and the device interface and molecule interface all are common. This is common interface for material simulation, molecule simulation, and device simulations. Now, when I click on the crystal option, there is an option called, this interface is there, crystal builder. Now here you can select the type of space group. Let's suppose you want to make, I'm selecting from scratch. So as an example, you want to take, let's suppose I want to take this one. Okay. I want to take this space group 225 FMC face centered. And this is the A value, that is cell length A is equal to, let's suppose I want to give 4.07. And then I can click on this element. I can add the fractional coordinate points and then click on this. And this is the default element where I can click on the element 1. I can click on this carbon element. And once I click on the C button, C stands for carbon, the default element. So in the default element, if I will click on it, it will open the periodic table. From that periodic table, I can choose the elements. Let's suppose I want to make a simple gold crystal. So I have to find the gold from this periodic table and I will replace the carbon with the gold. So let's suppose it's gold is here. I select the gold and click on OK. And then I will click on preview. Now this is a face center cubic structures. So once I click on it, it will show here the fractional coordinate point at 0, 0, 0, P1, P1, P2, P3. And this is primitive cells. We can also see the conventional cells. This is for conventional cells view. And this is for primitive cells view. Click on preview. And if you want to see the symmetry operators, this is space group details, symmetry operator in formation of this particular crystals. And then I will click on the add button. So where is the add button? Let's see. Add button is near about. And there is a build button. So I will click on build. That will add this crystal in our library. So this is simple crystal where I define some cell length A value only. But we can also make the complex material as well. So if you want to make other combinations, so let me try to make some other complex material. So I will go to the file option and then click on crystal options. And let's suppose you want to take some other elements. So I want to take this simple cubic with 195 space group and this A as an example. I'm creating the new material from scratch. If you have your own material file, then you can also upload. And then I define the cell length A value. And then I will add this fractional coordinate points. So I will click on this and click on this carbon element P1, P2, P3, fractional coordinate point is equal to 0. And then click on again. And I will add this value. And then again on this carbon plus button. And then add this value. And then again, I will click on let me select this one. So I'm trying to build one crystal structure from scratch. So I'm adding the element name, their coordinate points. So now I want to click on this final one. So in this ring shape, I want to make it. So you can see here, this is like, let's suppose one of the crystal. So what I did here, I simply select the space group, let it simple cubic and their A value, and then this coordinate point of all the default carbon. If you want to change any carbon element, you can double click. And if you let's suppose you want to change with boron, you can select with boron and it will show the preview of the borons. So based on that, whatever you have selected, accordingly it will display. And if you want to replace the same, you can click on that and it will replace and show the same color so that you can identify it quickly. Now then you can click on build button. It will build your crystal in this particular manner. Now whatever other manipulation you want to perform, there is also full provision where you can see this top toolbar. This toolbar will help you a lot to model, to manipulate in your atomic structures. So let me do it some modification or some manipulation. We can also do that. Just a minute. Now, if you want to replace this particular atom, once you build your structure, and let's suppose you want to add the doping in this particular crystals. Okay. So what you can do, you can select particular element. So I selected this element by clicking on this element. Then there is an option called replace atom. On the top of the bar, you can find there is an option called replace atoms. So you can select here that element. If you want to add the doping, you can select whatever the element you want to replace and click on OK button. It will replace the elements. And if there is some bonding misbalance is there, then you can select all the atoms nearby. And in the last option, there is an option called recalculate linker bond. So if there is bonding is there, this magnesium atom is making bonding with other far atom, then it will show you we have clicked on this recalculate linker bond. There is a last option on the right top bar that is called recalculate linker bonds. So it will recalculate the bonding which the replaced atom is trying to make with other elements. So that's why this I click on it and it has created the bonding. If you will undo it, if something has happened by mistake or you don't want to do that, this user interface will help you a lot, where it can change in your previous positions. It can save a lot of your time so that you can majorly focus on your main objective, whatever you want to do. But the interface can help you to model your structure quickly. Now, this is one of the procedure where user can import the material from library, import the material from online source, or create the material from scratch. These 4 procedure I have explained you, 3 procedure I explained you, and the 4th one is called, you can upload your CIF file, XYZ file, XSD postcard file, quantcar file, SCF input file. These extension, including PY extension is also there, which can uploaded on this user interface directly. So that's why if some other extension is there, in this last option, you can convert this your existing file in this HZW or XYZ, and it will upload indirectly in the software. So there is a directly option is there, and indirectly alternative option is also there, so that instead of creating your material from scratch, you can directly work on the software capabilities. Now this is all about the material building, material uploading, material searching informations. Now, if you see here, there is an option called build. This build option will help you to build your structures, to manipulate your structures, to make the supercell, to make the surface structures, to make the grain boundary, nanotube, nanowire, disordered graphene, zinc blend, and interface structures, get to atomic, molecular 2D decomposition. Many more things are there, including the top toolbar. That toolbar will help you to mirror, to add the vacuum, to measure the distance, angle, dihedral, plane, convert your molecule into materials, hydrogen passivation, bond length measurement. So many more things will be there, because it is not a one-day part. It's a complete package where you will get to know many things. Now materials uploading is done. Let it try to simulate one material, and then we'll see some output. So apart from material, let it go to the simulation of the materials. For the simulation, I want to simulate this first material, which I uploaded in the beginning. That is called MOS2. So I click on this Rescu and click on SCF calculations. SCF stands for self-consistent field calculations, where I can also define the smearing sigma, resolutions, and there are 2 methods to simulate this material. Real space method is there, and LCAO method is also there, linear combination of atomic orbital and real space method. If you talk about the exchange correlation function, LDA PW, GGA PBE, LDA PZ, LDA BWN, and SOL and other exchange correlation functions are there, including some hybrid and meta GGA functions. So hybrid HSE06 is there, meta GGA is there. Dependent on your need, you can select the type of exchange correlation function and sampling points you can define. It will solve the charge density, total energy, and there is maximum step, SCF calculation 200 step. It will run the job. Mix method is there, multiple options are there in mix method calculation. Mix variable is there, linear option is there. And basis sets. In basis sets, you can find the double zeta polarized, single zeta polarized, and user defined basis sets is also possible. So by default, it is selected the double zeta polarized. But if you want to see the basis sets library. There is some neutral atomic database library also there, where each material's specific library there in our database. So whatever material you are working on it, single zeta polarized, double zeta polarized basis sets are available for each material mostly, including Havard U terms is also there. So LDA plus U with SPDF position, you can define it, and you can also run the calculations. And this is spin type, no spin without any spin polarization, with collinear spin, magnetic moment you can define, and general spin with spin orbital interactions. So rho theta phi spin orbit interaction is also there that you can include based on your particular needs. So let me try to simulate without any spin effect. And then I want to click on generate files. So once I click on generate file, it will generate our SCF input file for this MOS2 crystals. So if you see here, this is SCF.input file for MOS2, and default parameter you can visualize here. This is default parameter where whatever the result shape path, lattice vectors, eigensolvers, default solver type, k-point sampling, and some other domain specific parameters are there, and including the basis sets information directly loaded by defining this MATLAB format. And this is atom coordinate point. If you want to see the atomic coordinate points of molybdenum and sulfur atom, so 2 sulfur atom and 1 molybdenum atoms are there, and that coordinate point is here. So you can see here. And this atom.xyz file is already included in this main SCF input file, which you can see here, atom.xyz file that will call during the simulations. So we will simulate main SCF input file instead of atom.xyz file. So I want to right click SCF.input file and click on run button. We also have the provision for multiple coring. Since it is a demo license, so I want to run on single, but parallel calculation is possible. User can also define on multiple cores. So parallelization is also there. Now I want to run the job. So you can see the simulation has started. It will execute in the background. It is under processing. Once it is done, then we can visualize your output. So let me close it, and simulation is running in the background. If we want to go to the analysis part, I can click on the analysis options. So if I click on the analysis option, there is an option called band structure, density of state, molecular population, potentials. These are the 4 parameters in the basic electronic structure calculations. Since today is the first day, so I'm covering up the basic things, but the software is very advanced. Multiple tools we have. So I believe any of our software or equipment can meet your requirement definitely. So if you see this density of state, there is projected density of state option is there on particular element, atom, or local density of state is also there. So whatever type of density of state you want to plot, similarly the band structure is also there. Molecular population is there, potential is also there. So different potential, atomic potential, effective potential, Hurty potentials, neutral atomic potential, exchange correlation potential. These are the multiple type of potential is there. So user can select the type of potential, and then you can able to visualize the potential analysis, band structure, and density of states. So let me select the default one and click on generate files. And I have to run all my input files. So you can see the local density of state.input file is generated. So I will right click and click on run button and click on the run program. Similarly, the band structure.input file, I will click and click on the run button. Molecular.input file, click and then click on the run button. And potential.input file and click on the run buttons. So all whatever I wanted to select, I have selected all my analysis, and it will run the simulation here. My all analysis input file in the queue. So one by one, it will execute the program. Once the simulation is completed of each file, then we can also visualize our output in our visualizers. So let it run the job. If you see here, the calculation is running. The simulation is started here. So it will show the beginning time and finished time, and how much time it has taken the calculation. That will also display during the end of the sessions. So at 6 a.m. it is generated. Now it is running the job. It is executing. So one by one, whatever the simulation completed, it is showing the completed, and whatever the input file running, it is showing the calculation is running. And next it is in the queue. So it is showing the Q1, running one, and completed one. If you want to see the output of LDOS band structure, for that purpose, you go to the simulator and Rescu, and then go to the analysis plot. Once you go to the analysis plot, go to the desktop and go to the FDP, MOS2 crystal, Rescu crystal, and result folder. In the result folder, you can find this local density of state .text file. So these are the output file. So I can click on open and it will display your output. This is local density of state in 3D. This is 2D model. And if you want to see in the Bundy graph, this is one-dimensional along Z-axis. So one-dimensional, two-dimensional, three-dimensional, the output can be generated. Along average in XY plane, this is in YZ plane, this is in XZ plane. So dependent on different plane, the output will display. And this is plane display, and this is one of the stereoscopic display analysis. You can view your output, whatever the position. You can add or remove the space in the vacuum of the unit cell, dependent on your needs. And the 3D model is also there. This is for 3D. If something is there, it will display for 3D. For LDOS is also. Similarly, for other analysis, if you want to perform, there is analysis plot. This is hello, am I audible now?
Yes, sir. Yes. Yes, sir.
Hello.
Yeah, you are audible, sir.
Okay, fine. Thank you. So this is density of states. So we can also plot the density of state. You can see we can zoom particular region and with the minimum and maximum energy levels, and we can plot our output accordingly. So DOS, LDOS, PDOS, and other analysis is also there where the user can get these analysis. Similarly, if you want to see the potentials, this is for potential analysis. Only 2 atoms we have taken. In coming time, we will take more atoms and then we can visualize your other analysis. So this is for potential, neutral atomic potential. And similarly, the Bundy graph is also there. One-dimensional, two-dimensional, and three-dimensional models are there where the user can plot. So this is all simple basic analysis. Now, if I will work on these other materials, let's suppose this is boron nitride and aluminum nitride. So we will try to create some analysis, some Raman property and optical property. For Raman and optical property calculations, so let's suppose this is one of the material. Once the calculation complete, then pop-up will come. Pop-up comes up. So let's suppose you want to simulate this boron nitride. This is one of the boron nitride structures. So if you want to simulate this structure, you can go to the Rescu and go to the DFPT analysis. I show you the DFT theory, where all electronic analysis I selected. Apart from electronic property calculation, this is called the perturbation theory, which works for Phonon band structure calculation, Phonon density of state calculation, Phonon band structure and density of state calculation, optical property, and Raman property. So these analysis, let's suppose I want to calculate the Raman property. So I selected the Raman default parameter, and this is smearing sigma resolutions, and real space method is there in this DFPT. And there are two LDA and GGA method is there for Raman calculations. Iteration control is there, and this is the DFPT Steinhammer and CFSI. These are two solver that will solve the perturbation theory. Then go to the basis sets where double zeta polarized and some single zeta polarized, and user defined basis sets is also supported. So by default, it is selected double zeta polarized for boron and nitride, both of the element. Then go to the spin type, select if any spin is there. This is Raman intensity parameter, damping factor, viewpoint Cartesian, incoming photon, outcome photons, incoming photon wavelength, temperature. So these are all Raman input parameters. The temperature variations also, incoming photon wavelength, incoming photon polarization, and outcome photon polarization. And click on generate files. Once you click on generate files, it will generate the input file for the Raman analysis. So if I will click on mesh SCF input file and open the input file for this boron nitride, it will open all the script, all the code that is auto-generated from the user interface. So this is auto-generated background code that will run in the backend. So this is main SCF input file. And then if you want to see the dielectric input file, you can open, this is dielectric parameter input file, and similarly the Phonon and Raman one. So let me run the job. I can click on the run button and click on this main SCF input file, then click on dielectric, run the main dielectric input file, and then click on this run button and click on the Raman input file and run the job. So all the input file, whatever I selected, will be run one by one. If you see here, which input file is running right now. So you can indicate, you can identify here the DFPT SCF input file is running currently. Then we'll go to the next one. Now you can see once the main SCF input file finish the job, then it will show the pop-up. So this is a pop-up that one SCF input file has finished their calculations. That's why the pop-up comes. And then this is the next one, which is executing right now. So one by one, it will run it. Then we can also visualize our output. So it is running the job. In the meantime, let me try to build one small molecular structures also, because the calculation is already running. So I click on the build option and then click on the molecule 2D options. When I click on this molecular 2D, it is basically a molecular builder. This will help you to build your any type of molecules. So I click on this molecules. Let's suppose I click on this element. Let's draw aryl group. So I selected it, and this is now selected. Similarly, I select the single, draw single. I click on every points. One. Just a minute.
Sir, voice is not clear.
Sir, you are not audible.
So 1 minute, let's running, simulation is running. So just a minute. It is running the follow calculation. So it is taking some time. In the meantime, I will also run the job for this Al2O3. Sorry, aluminum nitride. So Raman property, and parallelly I want to run the optical property. So I will go to the basic setting and select the optical properties. And in the optical property also, smearing sigma, resolution, real space method, and this LDA and GGA, PW and PB, both options are there. Iteration control parameter, the DFPT solver is there, basis set is there, spin type, and optical property. This is for electrical field direction. So I can select it and click on generate. So one is called for boron nitride, and second one is called aluminum nitride. In this aluminum nitride, if you see here, the optical dot input file is generated. So I will right click, and if you want to see this input file back code, this is backend code for this optical one. So let me run this SCF input file for the optical analysis also. So I will right click and click on the run button. And I'm putting dielectric dot input file in the run, and phonon input dot file in the run, and optical input file, and click on the run buttons. So all the input files are running here one by one. And once the calculation are completed, then we can visualize our output. We can see the Raman properties, optical properties, and many more properties is possible to visualize. So since perturbation theory, Phonon calculation may take little bit time in the simulation, so you need to wait for that. Or we have many couple of projects is available in my library. So I will show you open project, and I want to show you a couple of existing project which I worked earlier, and that I want to show you here. Simulation is running in the backend, and these are many projects which I work on optical, Raman, and nano device simulation, transistor simulations on different projects. So we can show you these projects dependent on your needs. So different projects I already simulated. So if someone want to work on it, definitely I believe for atomic scale modeling, DFT material device simulation, these tools will be very beneficial. So the simulation may take some little bit time. If you see in the backends, it is running their job. The job is running already. And once this Phonon, because Phonon kill takes the time, and you require some workstations or Even if I run on the parallel, then it may execute fastly. And it is showing the top that how much time it will take or all the information. The job status, basically. It is showing the job status, total time, like that. Now you can see this Raman is completed. Now we have reached to this level. Okay, so Raman property analysis. Now we can visualize. For visualization of a Raman property, I need to open it, and I have to need one command. Sorry. I need one command here in this. So let me type rescue space -p space dot. In the result folder, it will load the main project. And save it. I type this command to plot my output. So that's why this P command I written, so that it will plot my output in MATLAB. I run this again, but it may take some time because some other program is executing. Because two programs I'm running simultaneously. So it is in the queue because we are running after this. So after this executed, then it will execute. So just to wait for that. But in the meantime, I can explore you many things. So if you see here, this is so many things are there where you can also redefine your crystal. If you made one crystal and that crystal you want to redefine. So let me take one material. In the meantime, I can show you some graphene related material, Maxine or kind of things. We can build it since the simulation is already running. So I have loaded this 2-atom carbon atom of graphene. If you see in this backend, this is 2 carbon atoms of the graphenes. To make a supercell, I will go to the build option and then click on the redefine crystal. So if I click on redefine crystal, let's suppose in A and B direction, I want to repeat it 30 times. So this A and B, that is called this vertical and G direction. I want to repeat 30 times. So this I repeated and it is now my graphene seeds. And then once preview is done, this is preview, I can click on build button. Now this is built for this graphene seed, which build in very quickly. And we can also simulate this kind of structures. Okay. Simulation is going, and if you see, this is single layer graphene seeds. If this sheet you want to simulate, you also have that provision. You can simulate it. Now, if you want to create the defect, let's suppose you want to create the defect, so you can select particular elements. So this particular element I selected in the yellow color, and I can press the delete button. Once I press the delete button, the defect can be created in the sheet. So by deleting particular atom, the defect can be created. Or if you want to, instead of default, instead of delete, you want to replace. So this structural defect, you can select particular element and click on replace atom. And then you can select this, let's suppose magnesium or any element from the periodic table, you can select and replace. Now the atom has been replaced, that you can see. And if you want to see either it is making the bonding with other element, we can select all the neighboring atoms by drawing the rectangle and click on right side recalculate linker bond. And then it will automatically find if it is making the bonding with other elements. So this kind of things can be done. If you want to measure the distance, we also have the distance measurement tool. This right top, if you want to measure the distance from one atom to another atom, center to center, let's suppose this atom you want to measure the distance, how much will be the distance. So this distance measurement is also there. You can see this particular element 2.842 angstrom. This is the distance in between these two elements. So distance measurement including some angle measurement is also there. If you want to measure the angle as well, you can select 3 elements and measure the angle. So I have selected these 3 elements and the angle in between these 3 elements is 60 degree. So angle measurement, dihedral measurement, plane measurement, vector measurements, and other measurement is possible. So the measurement can also be done with that. Now, if you see all the simulation is done, which I wanted to do, but the optical one, I also need to run this optical input file. So I need to type in the optical one, the Rescu. To plot the optical data, I need this command in this optical.input file. The name of particular material file and then mat file. So this is one command which I written to plot my output of optical data. So I saved this command and then rerun this optical input file. So my optical and Raman analysis will be completed. We will visualize our output. Now you can see this is IR intensity which you have seen right now. It was plotted. So I would like to plot you completely. So for that I need this, even in MATLAB also we can plot this data. So I want to load the project. I will browse the FDP project in my desktop, which we were working on it. So this is boron nitride. I will locate particular folder and select it. And there will be some file. 1 minute. So I want to show that data once not. So you can see here, I want to show this one. So this is like a Raman intensity with polarized Raman intensity. We can plot this data. You can see here. Okay. So Raman plot, polarized and averaged. This is Raman intensity. Even if I show you in the graph our results, so 1 minute, FDP, boron nitrides, Rescu, and I will select it. And this particular path, we created the folder FDP, boron nitride and Rescu. So if I click here, this is the Raman intensity analysis. Okay. And similarly, the Raman plot along the average directions. And this is I1, I2, and I total. And for optical analysis also, we have that folder, aluminum nitride. And this is the If I click on it, this is the dielectric permittivity and energy. And this is energy graph, which is calculated for Al2N2. Similarly, if I click on it, this is the IR intensity with respect to energy, IR intensity. And if you want to see it, this is the energy loss with respect to energy. And if you want to see the refractive index, real imaginary part of MK data, this is the refractive index of MK value. So all electronic property calculations, Raman property calculation, optical property calculations, and density functional theory and perturbation theory. Specifically for all material analysis, the software can be very helpful for that particular scenario. Even many more things are there which I could not able to explain in one and a half hour. So I just request to the participants which can visit our YouTube channels. So you can type our YouTube channels, this by name, Impulse Technology, Innovate Your Research. In your Google YouTube, you can type this name, Impulse Technology, Innovate Your Research, and find this channel there. And in the channel, you can see this is our YouTube channel, and go to the playlist. In the playlist section, there is one Rescu. In this right side, there is a Rescu software full playlist are there. So you can watch this playlist where many more things are explained in details. So once you will watch these video related to Rescu, I believe this will give you insight more about this particular material property prediction tool. So please watch this playlist, which I can also share on the chat box. Which I can share you on the chat box. So you can click on it, you can subscribe. Now from my side, I have tried to explain many things, but if you want to see the documentation page, this is one of the website, nanoacademic.com. In the nanoacademic.com, you can find on the bottom of the page. This is bottom of the page of this website, nanoacademic.com. In the documentation section, you can find the information about the Rescu package. So once you click on this Rescu, you can find all the getting started tutorials where you can work on different tutorials analysis. So you can click on it, you can work on it, and different theoretical information is also given. How to getting started with different syntax, accuracy, band structure, band unfolding, boundary conditions, DFT plus U, perturbation theory, Hubbard functions, parallelization, spin DFT, STM is also there. So many things are there. Please read the manuals and watch our YouTube channels. I believe this will help you a lot, and many more things will cover up in the coming session. From my side, 1.5 hours is okay, fine. Now I request to the participants, you can unmute your mic and you are free to ask your questions, please. So participants can unmute your mic and you can ask your questions.
From where can we get more information about this Rescu software? I mean, if we are willing to use it for our materials.
Yeah, can you please repeat
I just like the software which we have just administered to us. For more information regarding that and more tutorials, as I work on materials, and exactly the same DFT calculations are useful for me. So from where can I get it?
Which information?
Like more tutorials and about the package as well.
Basically, many things are given on this documentation page, and video is also there. If more information are required, then you need to keep in touch with us. Okay, we have some more package, then we can also share you by emails and something like that. Because it is also enough. If you will scroll this information, documentation and video, that is also good enough. Even beyond that, if you want to work on something, then we can also try to help you.
What was the website you just told? I actually missed that part.
This is called nanoacademic.com. So I can refer you the documentation page. This is the documentation page, which I can post on the chat box link. And this is our YouTube channel. So I can give you our YouTube channel information, where many content is available freely.
Excuse me, sir.
Yeah, please.
Sir, is there any possibility of device interface study like two metal oxides can be added together and interface study is possible here, sir?
Yes, it is definitely possible. So if you want to work on interface heterostructures, that is also possible. If you see, there is one provision called, if you see here, build option, there is interface builder. Okay. So in this interface builder, you can also make two materialized interface, and it can create the heterostructures.
So heterostructures up to quaternary, levels can be created, like.
Yeah, if the same lattice type is there, if both the material are same lattice type, then you can also create the heterostructure. Let me take two materials. So if I take as an example, let I take one of the material as an example, gold. Okay, and second material similar lattice type. Lattice types should be similar so that the lattice mismatch should not come. And one is silver. So I taken these two material. You can see the AU.HZW and AG.HZW. These two material I have imported from my library right now. If I want to make the interface, I go to the build option and go to the interface builder and select the materials. I selected the gold, and second structure B, I selected the silver. Define the strain or something like. Click on this match and see the preview. So this is like here you can see the number of atoms, mean absolute strain in percentage. So based on selected number of this strain, it will match this one, and it will click on preview. So this is like you can see the total number of atomic number, angle, rotations, strain data, and based on that you can create your interface, and then you can click on build. The interface will be created. So like I created two metallic elements. Similarly, whatever other element are there is no problem. If the lattice is same, the interface can also be built.
Okay, sir. Thank you.
Yeah, hello, sir. Good evening, sir.
Yeah, good evening, please.
Sir, it was very nice presentation for our solar cell and different software. Sir, actually, I'm working on perovskite solar cell, especially for optical absorption or light absorption in the active level. So how it will be useful in that, sir? How the material property can be used for absorption of the lights in that?
Basically, this software can work only for material property prediction at atomic levels. Okay, let's suppose you want to work on perovskite. So this is like layer material, nobility material, perovskites. So these are some different perovskite material is given in our library. Okay. So if you want to simulate these perovskite material and their electronic property, phonon property, Raman property, optical property, it can calculate. Even atomic based device simulation can also be simulated to photodetector. But when you are talking about the layer based optical absorption, that how the light will get absorbed by your perovskite solar cells, then we have one of the another software which I want to introduce you about this SETFOS. So we will cover up the demonstration on SETFOS also. I think specifically on perovskite application. So one of my colleague will discuss on the perovskite demonstration on solar and optical analysis. That will be on 28th. So if you see this brochure, this 28th perovskite solar cells, how this kind of layer-based structure apart from atomic waste structure. But this tool is for atomic waste material and device simulations, not for layer based
Okay.
drift diffusion. So this is for DFT calculation tool, and another tool that will be presented on 28th, that is drift diffusion based solver. So these are two solvers
Okay.
dependent on your particular needs. It can whatever the tool is benefited for your research, you can choose accordingly.
Yes. Excuse me, sir. At the starting only, in some slide you have shown about stability checker. What is that? Could you please elaborate? The stability checker and other things.
Right. So for the stability of perovskite application, we have one equipment. So the equipment name is called this little slide. This one. This is one of the instrument, and this instrument will basically parallel JB and stability measurement platform for solar cells. So parallel JB, stability test, ISOS protocol, MPP tracking, solar simulator, and custom made sample holders. So this one is for parallel JB and stability measurement tools.
Sir, in your company, if you want to do experimental research, is it possible there? How it's possible? Simulation we are doing, suppose software, but if you want to do some experimental research for like 15 days or 30 days, so is it possible?
These equipments are need to be purchased.
Excuse me, sir.
You have to purchase these instruments. If you want to do experimental, then you have to purchase the instrument. Even the software is also, the demo license is available, but it need to be purchased. These are all commercial software and equipments which need to be purchased by the customers.
But I think this software is not for single user, I think.
For which instrument? You are
So this software is not available for student. I think it's institutional license.
Yeah, it is institutional, exactly. Not for individual. The institute need to be purchased. Exactly.
Okay.
So you can see this, choose the right for solar cell stability. So we fit all the conditions.
Okay, thank you, sir. Thank you for this.
Good evening, sir.
Yeah, good evening.
Sir, in that Rescu software, is there any facility available to find the stability of any of the materials?
With practice point of view, you have to do your own research, and many papers are published using the software. So papers are published in good journal, so you have to validate your results. So there is no directly option to validate or find the application.
Okay, and the second thing is that so you thought about the Rescu and its optical properties, DFPT, etc. So is it possible to measure the thermoelectric effect or conductivity, etc.?
Yeah, so that session we will come up by tomorrow. That will be for on Nanodcal software. So tomorrow session I will discuss on thermal conductivity or thermoelectric properties and device properties, nano device, transistor simulations. So this tomorrow session we will discuss.
So, okay. So that is for the Nanodcal, no?
Yeah, that is good.
Okay. I'm getting a bit confused. The Rescu is different and the Nanodcal is different, or?
Yeah, these are two modules, these are two calculation engines, the same software. So Rescu works on material property with advanced functionals are there, including response functions that Raman and optical analysis. And Nanodcal is also one of the tools which can also work on material calculation based on density functional theory, and NEGF is also implemented, non-equilibrium gain function for device quantum transport calculation.
Okay.
So that we will discuss tomorrow, that how this Nanodcal. You can see in the same package. Let's suppose some people work on material only. They don't want to work on device only. Or they want to work only with structure, Raman optical. Then they can buy only Rescu package. But those works on multiple applications. Then we have a Nanodcal plus Rescu bundle package is also available. Dependent on the customer requirement, we have different options.
Okay. Suppose if I want to work for what is called the thermoelectric properties and all, especially for the 3D materials, bulk materials. In that case, I have to get the Nanodcal plus Rescu.
Yes, definitely. Yeah, definitely.
Okay, thank you, sir. Thank you.
Hello, sir.
Hello.
Sir, is it possible to staking the layers and twisting one layer, making the wire patterns?
Yes, twisting is also possible if you want to twist the layers. So if you see this is, let's suppose, one graphene structures. Okay. And if you want to create the twisting or buckling, whatever the things you want to do, it is also possible. So twisting, I can say you, let's suppose this is one graphene cell, and let me zoom it. Okay. If you want to select some of the elements, let's suppose this element you have selected. If you want to rotate it, this is called the rotate option. You can rotate clockwise, anti-clockwise, and particular angle, 30 degree, 40 degree, 50 degree. So twisting is also possible. You can twist the atom positions. Even
Thank you, sir.
particular selected element, if you want to create the buckling, that is also possible to create it.
This is for one layer. I'm talking about staking the two layers, particularly one layer. Can we twist the one layer?
Yeah, you can also create a two layer. Let's suppose this is single layer. I selected this layer and you want to create the mirror of the same structures. So this mirror is also available, where you can create the mirror in particular direction and the two layers can be formed like that. You can see the two layer has been created quickly.
Okay.
So bi-layer, single layer, mono layer, dependent on your needs, you can create it. That's why the toolbar option is there, which I could not explore everything, but this 5-day session is there. So you will definitely get to know many more things in coming days.
Thank you, sir.
Yeah. So any other participants have a
Good evening, sir. So I wanted to ask one thing. What about the indoor application, sir? Like we are doing indoor application for perovskites also. So light requirement is very low. In minimum light, we have to design the structure such that internal reflection is increased. What is the setup for that in this particular tool?
let's suppose you want to work on indoor PV application kind of things, right?
Yes, sir.
Okay, so I think I suggest this SETFOS can be helpful for indoor PV application. But how it can be done, I will have to more communicate with our developer. So it will be better if you can share your queries in the details to me, so that I can ask to developers also that how.
Yeah, mostly the more paper I've read, they are telling about adding some kind of corrugation kind of structures or some like hexagonal structures you introduce like that. Since it can be modified in atomic level, so I'm guessing that it can be done in this tool, like including this corrugation kind of structures in the surface level.
I have to check it on, like, you can type your application as well as the tool name on the Google Scholar page. If somebody have worked on it in past, then let's suppose you are looking for Nanodcal plus indoor PV application as examples. If something is there, somebody published the papers, then you can find it. So you can see many people have like quoted something. So you can send me your query in detail. So I will look into that. Then probably in coming days I can better answer your questions.
Okay, sir. Thank you. I'll get to you like personally.
Yes, of course. So I think let me see the chat box also. So the recording will also be provided. Even it is also available on our YouTube channel. And those who have some license problem, then we will look into that later on, because right now the time is also over, so I cannot show you. And how to convert the file, that I will show you tomorrow. Okay. Moore pattern is also there. Twisting the layer is also possible. So mostly the data can also visualize without MATLAB and MATLAB. Both options are there. Parallel simulation is also possible. People can also run in parallel.
Go ahead.
So rest of the thing is okay. If somebody have more specific query, then I request you can type your questions in my emails. Okay. This is my email address. You can note my email address and send me your questions. I will be happy to reply your queries, please. And I request to all the participants, kindly spread this information of the FDP to other your colleagues, students, supervisors, so that they can also attend it and get benefited. And tomorrow, please join at 5, same time, 5 p.m. And I will be deliver about the device simulation package, nano device simulation package, how it will be better than quantum X ratio or other simulation software, how we are better than. That will also discuss by tomorrow, specifically for nano academic product. So I believe this kind of MDP will be very useful for all the participants. So from I think today's session, it's good to know, and thank you for giving your time to join the session, and will please join tomorrow the same session. Okay. Now I am going to disconnect the session. Please come tomorrow. Okay. Thank you very much.
ಅಲ್ಲೇದಂತ